You hit enter, and the page loads. To the human eye, navigating the web feels immediate, a simple keystroke conjuring data out of thin air. Beneath that glass screen lies an incredibly complex and physically fragile architecture, billions of separate machines constantly coordinating to pass fragments of data across oceans and continents. To manage this chaos, engineers rely on the Open Systems Interconnection, or OSI model. It dictates how devices talk to one another and identifies where those communications are vulnerable to interception. This exact 7-layer protocol stack has governed nearly every piece of network traffic since the early internet. The screens we look at have evolved, but the underlying rules of transmission remain. If we freeze time the moment you initiate a single web request, we can track your data's descent through all 7 layers of this framework. Tracking this exact path reveals the mechanics of modern global communication and exposes where the system is most vulnerable to attack. The journey starts at layer 7, the application layer. This is the interface closest to you. It takes your interaction with a browser and formats it into an HTTP request. Your request immediately undergoes encapsulation. The raw data payload is generated and wrapped in an initial instruction header, marking the start of its descent. It drops to layer 6, the presentation layer. This acts as a universal translator, formatting your request into a standardized syntax. This is also where your data is secured. Using protocols like TLS, the formatted payload is encrypted, turning readable text into a secure cipher. At layer 5, the session layer takes over. It opens an active, synchronized line of communication with the destination server, ensuring the connection stays alive long enough for the data exchange to occur. Your input is now a secure, standardized package, but at this stage it is entirely software, with no physical means of leaving your device. To prepare for transit, the data drops into layer 4, the transport layer. Here, protocols like TCP take control, prioritizing flow control and delivery confirmation. Sending the entire file at once would clog the network. Instead, the payload is precisely partitioned into manageable, uniform pieces called segments. A TCP header containing specific port numbers is attached to each piece, ensuring the destination server knows which application the data belongs to. The segments fall to layer 3, the network layer. This introduces global navigation and logical addressing. The layer wraps each segment with source and destination IP addresses. These packets now carry the exact geographic coordinates they need to navigate the global internet backbone. They're directed by massive clusters of autonomous physical routers. These machines read IP addresses on millions of packets a second, calculating the most efficient path. By dividing the payload into independent packets, the network ensures survival. If a router goes offline, the packets automatically find alternate routes to the same destination. The packets eventually reach your local network, dropping into layer 2, the data link layer. Global routing ends, and local node-to-node delivery begins. The packets are encapsulated one final time. MAC addresses and cyclic redundancy checks are added to detect transmission errors, transforming the packets into frames. Finally, the frames hit layer 1, the physical layer. Software abstraction ceases completely. The data must become pure physics. The network interface card translates the digital frames into raw binary bits, ones and zeros expressed entirely as alternating electrical voltages or radio frequencies. These bits surge at the speed of light, racing through the dark glass core of a fiber optic line. Maintaining this physical transmission requires grueling labor and thousands of miles of heavy undersea cables dragged across the ocean floor. This global network is anchored by the physical reality of copper, glass, and light, making the physical layer the foundation of all communication. At the destination server, the process systematically reverses. In milliseconds, headers are stripped, packets are reassembled, and the payload is decrypted. The decapsulated data is finally rendered by the application layer. On the receiving screen, your message simply appears. Cybersecurity professionals interpret the internet through the lens of this layered matrix. Threat actors design weapons targeting specific vulnerabilities within this architecture, such as Layer 3 DDoS attacks to overwhelm routers, or Layer 7 scripts to compromise applications. Defense architecture works by isolating these patterns, projecting firewalls to terminate attacks at the specific structural layer where they occur. By breaking global communication into these 7 distinct layers, the OSI model provides the necessary map to build and defend the modern internet.